Hi everyone and welcome back to Causality with Boris, broadcasting from Sobolev Spaces. In this video I talk about comparing observed and counterfactual risks. The main focus will be on a different use of counterfactuals. I'll present a case in which we compare the world as is with the world as it might be. Now, be sure to watch to the end, so that you can compare the takeaways with your notes. There will be extra material for this video. Click the link in the description and it will be sent to your inbox. It's relatively simple to describe what's causation. One event brings about another event. Cancer treatment prolongs life. Immunization prevents viral transmission. It's difficult to establish it. We see two events, but we don't see a causal relationship. How do we know that one event causes the other? It comes from reasoning. The key idea is that both covariation and causation manifest as association. How can we rule out covariation? We looked at the network of dependencies between factors in play. We examine how they affect treatment and outcome. We applied graphical criteria to see if treatment effect can be identified. We then estimated by adjusting the observed effect for the differences between study groups. This approach is based on the idea of comparing changes in the same unit after application of different treatments. Each unit gets two potential outcomes, one for each treatment option. The population level effect is the contrast between these two sets of potential outcomes. We compare outcomes of one treatment with outcomes of another treatment in the same units. For the population effect, we find difference between the marginal risks. We think of marginal risk as the proportion of the population that would have developed outcome if all units received the same treatment. I will illustrate this idea with a mosaic plot. It represents the population of units. All outcomes occupy the total area of the square. For simplicity, let's assume that treatment response is either failure or success. Successful outcomes fill some area. To show it, we divide the square horizontally into parts. The colored area represents success. Its height is the marginal risk. But we need two squares, one for all treated units and the other is for the same units but not treated. Then the treatment effect is the difference between the risks plotted in these two squares. In this reasoning we use counterfactuals. The same study population is considered for alternative treatments. Counterfactuals is a powerful tool of causal inference. They help to address the most difficult problem of causal attribution, comparability of treatment groups. You see, we always concerned that differences in outcomes between treatment groups could be due to other factors. This problem doesn't exist though when we compare marginal risks in identical study populations. We're comparing like with like. In public health though, policymakers rarely frame questions as contrasts of two counterfactual situations. Rather, they compare observed situations to a hypothetical scenario. They are comparing the real and the counterfactual. They are comparing the world as is with the world as it might be. The most common what-if question concerns the risk reduction if exposure is eliminated. Take for example the seatbelts policy. Seatbelts protect people from death and injury. But many people don't wear seatbelts, whether they are in a hurry, distracted, or simply forgetful. Thousands die as a result. Seatbelts prevent the driver and the passengers from being ejected during a crash. 3 out of 4 people who are ejected die from their injuries. Seatbelts significantly reduce the risk of death and serious injury among drivers and front seat passengers. Mortality is reduced by 45% and the risk of serious injury by 50%. It's estimated seatbelts saved nearly 13,000 lives in the United States in 2009. Policymakers expect that increasing their use would save thousands more. If all drivers and passengers had worn seatbelts, nearly 4,000 more people would be alive that year. Counterfactual in nature, this estimate compares the observed situation to what might be if everything else remains as observed. Except that every person in every seat buckles up on every trip. Risk reduction that would be achieved due to reduced exposure is the most common type of what-if questions in public health policy. This is sometimes expressed as proportional harm reduction due to reduced exposure. Here are some examples. Reducing side effects by changing dose of prescribed medications. Preventable future treatments if patients had bypass surgery instead of angioplasty. Avoidable strokes if patients had angioplasty instead of bypass surgery. Preventable disability if patients had surgery within 2 days after their hip fracture. Let's illustrate this new idea using a Gann mosaic plot, but with some modifications. As usual, X denotes treatment and Y denotes outcome. X encodes the treatment group as 1 and the control group as 0. An indicator variable Y is 1 for the outcome occurrence and 0 otherwise. For simplicity, the outcome of interest is treatment success. Imagine that the unit square on this graph shows the study population. The blue area represents all successful outcomes. Its height is the probability of success in the study population, and if it consists of 2 treatment groups, the blue area is the average of the probabilities of success for each treatment. These are the rectangles, orange rectangles. If you take the 1 in 3 risks times 3/8, and that's the prevalence of the treated group, and add that to the 1 in 2 risk times 5/8 for control group, you get a 7 in 16 probability of successful treatment outcome. Now, treatment groups can differ in other ways, not just by treatment they get. Let's say there is a factor Z that takes 2 values, 0 and 1, and its distribution is different in the control group than in the treatment group. Each group still makes up half of the study population. This graph shows the existing risk pattern for the combination of the treatment variable and variable Z. If Z is 1, the risk in the treatment group is different than in the control group. But we still observe the average risk for the entire study population. Policymakers ask about the potential reduction in the risk due to eliminating harmful exposure in a given population. This means that the distribution of Z remains the same, and the risks associated with its presence will remain. Only now the entire population would not be exposed. So instead of comparing the green areas in the 2 squares at the bottom, we looked at the blue area at the top and 1 green area at the bottom. The counterfactual risk is compared with the existing risk patterns. To summarize, causal analysis of treatment effects looks at 2 hypothetical scenarios, all treated and all untreated, in the same population. Why hypothetical? Well, in reality, some are treated and others remained untreated. In a thought experiment, we looked at the potential outcomes of counterfactual treatment alternatives. Suppose Y1 of U is the potential outcome of treating unit U, and Y0 of U is the potential outcome if the same unit U remains untreated. The treatment effect then is the risk difference between population receiving and not receiving treatment. In the case of harmful exposure, we talk about risk reduction after complete elimination of exposure. In either case, we are comparing 2 hypothetical populations. We are comparing the counterfactual risk of P1 and the counterfactual risk of P0. Both are the averages of potential outcomes. In a thought experiment, we consider counterfactuals. These are imagined alternatives to the observed reality, not the world as it is, but the world as it might be. Counterfactuals are our way of seeing beyond the data. Without them, we would be forever describing what happened in the past. Yet we can also use counterfactuals to compare what is with what isn't there. You see, many policies look at existing and hypothetical risks. They are trying to figure out how much risk reduction could be achieved by eliminating exposure in the existing population. How many injuries could be prevented if everyone buckles up? How many repeat procedures could be avoided if all patients undergo bypass surgery for heart disease? In doing so, they compare the hypothetical population to a population with an existing risk pattern. Using data, we can compare the observed average risk to the counterfactual risk. The first is simply the average of observed outcomes, and the second is the average of potential outcomes. They are from the same population in which all other factors remain unchanged, excluding the exposure. Here's the main message of this video. The most common what-if question concerns the risk reduction if exposure is eliminated. You learn that we can use counterfactuals to compare existing risks with counterfactual risk, to compare what is with what isn't there. Don't miss the key idea that all risk patterns will remain the same. You watched another episode of Causality with Boris. Keep on watching.